Hello everybody, let's talk about section 7.3 on simplifying complex fractions. And despite the way that it looks, complex fractions are actually just taking some of what we've already done and making it taking it one step further. So I guess we need a definition right here. When we talk about what a complex fraction is, well, we say a complex fraction is a fractional expression in which the numerator and denominator both contain one or more fractions. And for our purposes, we're only dealing with rational expressions, so we're talking about rational expressions that contain fractions. Well, some examples, of course, are shown below here. 1 plus 1 over x divided by 2 minus 1 over x. You see that there are two separate expressions in the numerator and denominator that we would have to separate and simplify. Same thing with the next example. So the goal is to simplify the complex fraction by rewriting it to eliminate any fractions contained in the numerator and or denominator. And I'm going to start out with a numerical example right here. I've got 3 plus 5 halves over 8 minus 7 halves, and I want to simplify that. There's actually two methods. I'll show you the longer method, as far as I'm concerned, the longer method, which goes a little bit like this. In order to combine our two fractions, this method states that we should add the fractions together in the numerator and denominator so that we can get a single fraction over a single fraction, and then take advantage of the rule that says that anytime we have a over b divided by c over d, we invert and multiply our denominator fraction to make it a over b times d over c. All right, so let's just do that with this one so we see it in action. That means that if I have my fraction 3 plus 5 halves, I've got to get a common denominator. So I'm going to make it 6 over 2 to replace the 3, plus 5 over 2 in the numerator. And in the denominator, I have 8 over 1, so I'm going to make that 16 over 2 minus 7 over 2. And that becomes, simply enough, 11 halves in the numerator, divided by 16 minus 7, which is 9, over 2 in the denominator. And by our rule above, that means 11 over 2 would be multiplied by 2 over 9, and our result is, if the 2's are canceled out, 11 over 9. Okay, so that's method 1. You say, well, it actually doesn't seem that bad. How about method 2? Well, method 2 actually puts us on the fast track a little bit here. And what it does is this says that if we've got a fraction over a fraction, it is sometimes more efficient to multiply through by the least common denominator of all of the fractions in the expression. And we have 3, which is the same thing as 3 over 1, plus the fraction 5 halves in the numerator. We've got 8, which is the same thing as 8 over 1 in the numerator, minus 7 halves in the denominator. And out of all of those fractions, it looks like the least common denominator would be 2. And so what we're going to do here is that in the numerator and denominator, we're going to multiply through by 2. Right? Remember, if we multiply by 2 over 2, it's the same thing as multiplying 1, so we don't change the value of the fraction. But this time, that 2 gets distributed to both of the terms in the numerator. So this is equivalent to writing 2 times 3 plus 2 times 5 halves divided by 2 times 8 minus 2 times 7 halves. And the advantage of this particular method is that very quickly we get 6 plus, if you take 2 times 5 halves, the 2's cancel, leaving you 5. And the denominator, 2 times 8 is 16. And the 2 here cancel, leaving us with minus 7. And we directly get 11 over 9 without having to carry out this multiplication division step. So this is actually very direct if you remember how to do it. And that's what we'll do with our next example. Let's say we want to simplify this complex fraction by rewriting it to eliminate any fractions in the numerator and denominator. And so I would identify, if I look at all my fractions, 1 over 1, 2 over x, 8 over x squared, that the least common denominator of all of the terms was equal to x squared. So that's what I'm going to multiply into the numerator and denominator equally. Let's see what happens. If I take 1 plus 2 over x minus 8 over x squared, and I divide that by x squared, notice that it's like multiplying by 1, right? Any number over itself is equal to 1. 1 plus 3 over x minus 10 over x squared. Now we distribute. X squared times 1 is just equal to x squared. This is just in the numerator now. If you take x squared and multiply it by 2 over x, you're left with plus 2x. One of the x's cancels out. And of course, x squared multiplied by 8 over x squared is equal to minus 8 here. Do the same thing in the denominator, x squared times 1. X squared times 3 over x, that's 3x. And x squared times negative 10 over x squared, that's minus 10. And now we're in a better position to simplify this fraction if that's at all possible. And that's what we're going to do. Now we can simplify by factoring. Okay, so carrying that out, in the numerator, our two factors look to be, let's see, two binomials whose leading terms multiply to give us x squared, whose constant term, negative 8, factors as positive 4 and negative 2, which would give us x squared plus 2x minus 8 when we FOIL, and a denominator that factors as, it looks like, x times x for our first terms. Factors of negative 10 whose sum is positive 3 would be positive 5 and negative 2. And lo and behold, we do have a common factor that can be reduced out. And so our reduced fraction in this case is x plus 4 over x plus 5. And provided that x does not equal 2, it is completely equivalent to the expression above. More in the next video.